All right, so we're starting with chapter 5, lesson 1 on monomials. So what we're going to learn in this lesson is we're going to learn how to multiply and divide monomials and use expressions written in scientific notation. So some of the vocabulary to keep track of is a monomial, what is a constant, what is a coefficient, what's a degree, what's a power, what does it mean to simplify, what is standard notation, what is scientific notation, and dimensional analysis. So why is scientific notation useful in economics? So economists often deal with very large numbers. For example, the table shows the US public debt for several years in the last century. Such numbers written in standard notation are difficult to work with because they contain so many digits. Scientific notation uses powers of 10 to make very large or very small numbers more manageable. So here they kind of give you a visual representation. In the year 1900, the U.S. public debt was 1.2 billion, and then it got to 16.1 billion, and then it grew to 284.1 billion, and then it started getting into trillions. So you have 3.2333 trillion, 5.674 trillion. And so you can see that numbers get bigger and bigger in different things, especially in economics or if you're measuring stuff in space. So, or some numbers might get really small. Say you're dealing with biology and you're dealing with really small things. So on a macro, very large, and a micro level, you deal with very large figures, which scientific notation helps you kind of represent those things in a much more efficient way. So what is a monomial? So this is our first vocabulary word here. A monomial is an expression that is a number, a variable, or a product of a number and one or more variables. Monomials cannot contain variables in denominators, variables with exponents that are negative, or variables that are under radicals. So what does that look like? Well, here's an example of what some monomials look like. 5b is considered a monomial because it's just the product of a number and a variable. Negative w is a monomial. It's just the product of negative 1 times w. 23 is a monomial because it's just a number. X squared is a monomial because it's just a product of x times x. 1/3 x cubed y to the 4th is also considered a monomial because it's just the product of 1/3 times x times x times x times y times y times y times y. It's just a product of numbers and variables. And product meaning multiplication. So what are not monomials? These are examples of things that are not monomials. You cannot have a variable in the denominator, right in the bottom of a fraction. You cannot have a variable with under a radical. X plus 8 is not a monomial because that's not the product of two numbers, that's the sum of two numbers. So a monomial does not contain addition. And monomials do not contain negative exponents. So a to the negative first power is not considered an exponent. Sorry, not considered a monomial because of that negative exponent. So constants, on the other hand, are monomials that contain no variables. So a constant is something that contains just a number like 23 or negative 1. So the other thing that we're going to talk about is what is a coefficient? A coefficient is the numerical factor of a monomial, right? So for example, in the monomial 5b, 5 is the coefficient. It's the number in front of the variable. For negative w, the coefficient would be negative 1 because it's negative 1w. For this monomial, the coefficient is 1/3. It's the number in front of the monomial, right? The next thing we're going to talk about is, here was an example here. So for example, the coefficient of m in the monomial negative 6m, the coefficient is negative 6. It's the number in front of the variable. The degree of a monomial is the sum of the exponents of its variables. So for example, the degree of the monomial 12g to the 7th h to the 4th would be 11 because you'd add up the exponents. So 7 plus 4 is 11. So this would have a degree of 11, right? The degree of a constant is 0. So if we look at these monomials, this monomial 5b has a degree of 1 because it's b to the first power. Negative w also has a degree of 1. The monomial 23, which is actually a constant, has a degree of 0 because there are no variables within the exponents. The degree of x squared would be 2. The degree of this monomial, 1/3 x cubed y to the 4th, is actually 7 because I would add up the exponents of the variables. And then lastly here, a power is an expression in the form of x to the n. The word power is also used to refer to the exponent itself. So usually exponent and power usually refer to the same thing. Sometimes we use them interchangeably. Negative exponents are a way of expressing multiplicative inverse of a number. So for example, 1 over x squared can be written as x to the negative second power. So a negative exponent just refers to the multiplicative inverse. So if it's at the bottom of a fraction, you would move it to the top of a fraction. So note that an expression that such as x to the negative second power is not considered a monomial because it would have a variable in the bottom of a fraction in a denominator. So here's the key concept. With negative exponents, whenever you're dealing with a negative exponent, it moves it to the bottom of a fraction if it's on the top, right? So this is like a to the negative n over 1, so it would just move to the bottom. Likewise, if you see a negative exponent in a bottom in a denominator of a fraction, it would move to the top. So this would become a to the positive n over 1, or just a to the nth. So here are some examples. 2 to the negative third power can just be represented as 1 over 2 to the third power. 1 over b to the negative eighth power, again, would just move to the top to become just b to the eighth power. So to simplify an expression containing powers means to rewrite the expression without any parentheses or negative exponents. So getting rid of the parentheses by applying the things on the outside and rewriting negative exponents as positive exponents. So that would be written like this. This one would be written like that. So let's look at an example. Let's simplify an expression that involves multiplication. So here I have this monomial times this monomial. So I'm going to go ahead and simplify this. So first thing I would do is I would take this and I could actually rewrite it in what we call expanded form. So really 3 times x cubed times y squared is 3 times x times x times x times y, right? X to the third power is x times itself 3 times. Y squared is y times itself twice. And then I have negative 4 times x, y times y times y times y, again representing x squared as x times x, y to the 4th, y times itself 4 times. So now I've written these two monomials in expanded form. I can see what it actually means. And so now I can actually rewrite this using the commutative property where whenever you're multiplying things, it doesn't matter what order you put them in. So I'm actually going to put the constants next to each other, right? The numbers. And I'm going to put all the variables next to each other. So I put all the x's next to each other, and then I put all the y's next to each other. And then it helps me rewrite this, right? 3 times negative 4, I know it's negative 12. X times x times x times x times x. X times itself 5 times is x to the 5th. Y times itself 6 times would just give me y to the 6th. So it allows me to rewrite this in a more simplified way. So this example here suggests the following property of exponents, which we're going to talk about next, is the product of powers. Whenever I'm multiplying two things with the same base, right, the same bottom number, or the same base, like a to the mth times a to the nth, that would equal a to the addition or the sum of those exponents, m plus n. So for example, if I had 4 to the second power times 4 to the ninth power, that equals 4 to the 11th power. Or if I had b to the third times b to the fifth, same base, add the exponents, gives me b to the eighth. So this is a product of powers exponent rule that we will continue to utilize. So to multiply powers of the same variable, add the exponents, right? Knowing this, it seems reasonable to expect that when we're dividing powers, you should subtract the exponents. It's kind of the opposite of it, right? So if I had x to the ninth power over x to the fifth, right, which means divide those, I should be able to consider that I could subtract them, right? I could do, and again, if I write it in expanded form, right, x times itself 9 times over x times itself 5 times, right? These would cancel each other out, just leaving me with 1 over 1. And it would leave me with these x terms still left. So x times itself 4 times would give me x to the 4th, right? Because 1 over 1 just simplifies, right? So that would leave me with x to the fourth, which would make sense, right? It appears that our conjecture is true. When we're dividing things with the same base, we could just subtract their exponents, right? Because 9 minus 5 would have given me 4. So that leads us to our next exponent rule, which is the quotient of powers. Whenever you have something with the same base and you're dividing them, you can just subtract their exponents. A to the mth divided by a to the nth is equal to a to the power of m minus n. So for example, 5 to the third over 5, which is 5 to the first there, would give me 5 to the 3 minus 1 power, or 5 squared. Or if I had x to the 7th power over x to the 3rd power, again, subtract the exponents, it would be x to the 7 minus 3 power, which would be x to the 4th power. So this is the second rule that we're learning, quotients of powers. So example number 2 asks us to simplify an expression using division. So p to the 3rd power over p to the 8th. And we're going to assume that p can't be 0, because if I had 0 in the bottom of a fraction, it would give me an undefined number. So we're going to assume that p is not 0. So p to the 3rd over p to the 8th, I'm going to go ahead and subtract them, right? So it would be p to the 3 minus 8th power, which would give me p to the negative 5th power, because 3 minus 8 is negative 5. So remember though, when I have a negative exponent, that would actually be just simply written as 1 over p to the 5th, right? That negative exponent would move it into the denominator. It's multiplicative inverse. Okay, so remember, when you have negative exponents, just move them down either to the bottom, or if they're in the denominator, you move them to the numerator, move them to the top. So let's go ahead and check and make sure that this actually plays out the way that we think. So if I were to write this in expanded form, right, p to the 3rd is p times itself 3 times, p to the 8th, p times itself 8 times. Again, I do my canceling, and it leaves me with p times itself 5 times in the denominator, in the bottom, right? So it does make sense that it should be written in that way. So again, this is just me writing in an expanded form and proving that my rule of subtracting the exponents when I'm dividing things with the same base works. You can use the quotient of powers property and the definition of exponents to simplify y to the 4th over y to the 4th. Again, just assuming that y isn't 0, because you can't have 0 in the bottom of a fraction. It gives me an undefined number. So the first method would be to use our subtraction rule, right? Where you're like, oh, quotient of powers means I can just subtract the exponents, right? 4 minus 4 would give me y to the 0 power, right? Y to the 0 power is actually equal to 1. Method 2, again, y to the 4th over y to the 4th, use it in expanded form, right? All the y's end up canceling out, leaving me with 1 over 1, which equals 1. So in order to make the results of these two methods consistent, we define y to the 0 power has to equal 1, right? Where, in other words, basically any non-zero number raised to the power of 0 is equal to 1. So anything to the 0 power is always equal to 1. This is something that people commonly make a mistake. We're like, oh, if I put something at the 0 power, it's going to equal 0, but it doesn't. It always equals 1. And it doesn't matter what your base is. If you raise it to the 0 power, it's 1, except if that base was 0, because you would end up having a 0 in the denominator, which doesn't give you a defined number. So again, 0 to the 0 power would be considered undefined. So the properties we have presented can be used to verify the properties of powers that are listed below. So again, we're going to suppose that a and b are real numbers and m and n are integers. So if I had any base and I have a power to a power, I could basically multiply those exponents together. So again, if I had a to the 2nd power to the 3rd power, this is the power to power rule, that would just give me a to the 6th, because a squared times a squared times a squared, adding the exponents would give me a to the 6th. Power of product, basically if I have an exponent on the outside of a parentheses, I can apply that exponent to everything inside. Again, if I had x times y in parentheses to the 2nd power, that would just give me x to the 2nd times y to the 2nd. Power of quotient rules, basically same idea. I can apply the exponent to the numerator and the denominator. So for example, if I had ab to the 3rd power, that would be the same thing, or equivalent to a to the 3rd over b to the 3rd. And same thing with a negative exponent, except with a negative exponent, you can flip it. You can do the reciprocal to make it a positive exponent, right? Because it would send this one to the bottom, this one to the top. And then you can apply your exponents like before, b to the nth over a to the nth. So an example of that would be if you had x over y in parentheses to the negative 4 exponent. Again, you could flip it upside down, so it would be y over x, and then apply the exponent of 4, so you have y to the 4th over x to the 4th. So with complicated expressions, you often have a choice of which way to start simplifying. So let's look at a problem. So we have negative 2x to the power of 3n over x to the power of 2n times y to the third, and all of that is to the 4th power. So one way you could do it is you could apply this 4, this exponent, and raise everything in here to the 4th power. So let's try that one first. So if I took this, I took the numerator and put it to the raise it to the 4th power, took the denominator and raised it to the 4th power, right? And then I could apply that exponent to everything inside. So negative 2 to the 4th power, x to the power of 3n to the 4th power, and then everything in the bottom, x to the power of 2n to the 4th power, and y to the third to the 3rd power, or to the 4th power. So now I've applied these exponents all in there, and now I can simplify. Negative 2 to the 4th power is positive 16. X to the power of 3n to the 4th power, again, multiplying the exponents would give me to the power of 12n. Same thing here, multiply the exponents, x to the power of 8n. Here, multiply the exponents again, y to the power of 12. And then the final part is, you notice that these have the same base. They both have the base of x. So I would take it and do x and then subtract their exponents. So it would be 12n minus 8n. So this would be the power of 4n. So 16x to the power of 4n over y to the 12th. Let's try a second method. What if we didn't apply the power first? What if we simplified the fraction inside the parentheses and before raising everything to the 4th power? So let's try that. Let's try simplifying everything inside first. So if I were to simplify everything inside first, I would probably deal with these two things that have the same base, right? I have x to the power of 3n divided by x to the power of 2n. So again, I would subtract those exponents, right? It would be x to the power of 3n minus 2n, which would be 1n. And now that I've simplified the parentheses on the inside, now I can apply that exponent to everything on top and on the bottom. So negative 2 to the 4th power is positive 16. X nth to the power of 4 is going to be x to the 4nth power. Y to the 3rd power to the 4th power is going to be y to the 12th power. And again, you can see that you get the same answer. One thing that you want to focus on when you're simplifying expressions, an expression is simplified when there are no more powers of powers. So basically when you don't have any more exponents to exponents. Each base appears exactly once, right? So here where I had these two with the same base, that would tell me it's not simplified until I only have each individual base only appearing once. And then all fractions are in simplest form. So for example, if I had like 16 over 8, I would want to simplify that to like 2 over 1. And then there are no negative exponents left. So this one doesn't have any more negative exponents. So you have to make sure that if you do have negative exponents, you move them into the right spot to make them into a positive exponent. Scientific notation. So the form that usually writes numbers, and we typically write things in standard form. So typically you're used to writing things in standard form. A number in scientific notation versus standard notation is when it's in the form of a times 10 to the nth power, where a is a number between 1 and 10, and n is an integer, and it could be positive or negative. So scientific notation is used to express very large or very small numbers. So let's look at some. So it says express the following number in scientific notation. So here I have 6,380,000. So normally my decimal point is here. Well, if I need to represent this number between the number in 1 and 10, I would move the decimal place 1, 2, 3, 4, 5, 6 places. So it becomes 6.8 times a million, right? And so that would give me a number between 1 and 10, but I need it to be times 10 to some power. Well, 10 to the 6th power is actually going to give you a million, which gives me the clue when I move the decimal place over. With this one, same thing, but instead I want to move the decimal place to the right. So I'm going to move it 1, 2, 3, 4, 5 places. So it'd be 4.7 times 10. And then it's 1 over 10 to the 5th power. But again, I want to write it as times 10. So I'm going to go ahead and write it as 10 to the negative 5th power. Now notice the difference between a positive exponent and a negative exponent. Positive exponents help us represent really big numbers. Negative exponents help us represent really small numbers, because when I multiply by 10, that's what helps me move the decimal place in the direction to represent a big number. And when I have a small number, dividing by 10 helps me move the decimal place in the correct direction there. So this is representing a large number or a small number, again using the exponents or the power of 10. You can use properties of powers to multiply and divide numbers in scientific notation as well. So let's look at a couple. It says evaluate and express the result in scientific notation. So here I have 4 times 10 to the 5th power times 2 times 10 to the 7th power. So again, I'm going to rewrite this because I can write, it's all just multiplication, so I can write it as 4 times 2 times 10 to the 5th power times 10 to the 7th power. Well, I know 4 times 2 is just 8, and 10 to the 5th times 10 to the 7th, again, add the exponents, use our exponents rule, that's going to be 10 to the 12th. Now let's do the same thing with this one. Again, I'm going to rewrite this using those associative and commutative properties. So I can do 2.7 times 3 and 10 to the negative 2nd power times 10 to the 6th power. And again, multiply those. 2.7 times 3 is 8.1. And 2 to the negative 2nd power times 10 to the 6th power, add their exponents, gives me 10 to the 4th power. So this would be my answer there. So that's how I can multiply numbers in scientific notation. So real-world problems often involve units of measure performing operations with units known as dimensional analysis. So here's an example of a problem, a real-world problem. It says light travels at the speed of about 3 times 10 to the 8th power meters per second. The distance that light travels in a year is called a light year. So in this problem, it says after the sun, the next closest star to Earth is Alpha Centauri C, which is about 4 times 10 to the 16th power meters away. So the question is, how long does it take light from Alpha Centauri C to reach Earth? Use the information to the left. So the first thing we need is we need our distance formula, which maybe you remember, but distance is just equal to rate times time. So we're going to use that. And since we're trying to find the amount of time, let's go ahead and take this equation and solve it for t. Well, the way that we do that, divide both sides by r. And so that would give me t equals distance divided by rate. Because I know my distance, which is right here, from the Earth to that Alpha Centauri sun, right, or the closest sun or star, and then my rate would be how fast light travels, which is 3 times 10 to the 8th power. So I'm going to put those numbers in there. So I got my distance, my rate, and so I'm going to go ahead and divide. Well, I can do 4 divided by 3. And 10 to the 16th divided by 10 to the 8th, right? 4 divided by 3 is going to give me approximately 1.333. And then 10 to the 16th divided by 10 to the 8th is going to give me 10 to the 8th, because I can just subtract those exponents. 16 minus 8 is 8. And so this would tell me that it would take about 1.33 times 10 to the 8th seconds, or if you do the math, about 4.2 years for the light from Alpha Centauri C to reach Earth, which is crazy. Anyways, that's how you would do a bit of dimensional analysis. Thank you guys for watching, and let me know if you guys have any questions.